And we're back in action. This time, we're going to summarize things that we've been learning, and we're going to create a SciNB page to define Einstein's theories of relativity. Now, you may have heard of these things before, and you may not really understand what it means yet, but we're going to summarize it so that it can at least be something that you can walk away feeling like you have some idea as to what Einstein was theorizing in these big, complex equations that he made. We can summarize it into some littler chunks of knowledge here. So let's just figure out how we're going to organize our science notebook page. First, let's make sure that you got that title up top. We're going to draw some diagrams to really define this idea of relativity. Then we'll compare and contrast general relativity and special relativity. And then we'll walk away with some mind-blowing facts. Whoa, yeah, sweet. Let's get into it. So, Einstein's theories of relativity. Now, this idea of relativity, it's kind of like you have relatives. They are related to you. They are similar to you in some way, shape, or form. And so let's start there. Now, let's consider this kind of thought experiment that we have a very special duckling here that lays a golden egg. Ooh. Well, we have explorers from this side of the bird that's going to sail towards the bird. And on the other side, they're also going to sail towards the bird. Now, when they go back to their people, they want to say, you guys will never believe what I just found. There is a giant duck that laid a golden egg. No way. Everyone's going to want to go see it. And so this person with the dark blue sails here, they're going to tell their people, oh, you need to head to the west to find the golden egg. And this person over here with the light blue sails, they're going to say, oh, you must travel to the east to find the golden egg. Now, for these groups of people, it would be correct for each one. Neither of these two people are wrong. That the golden egg is not to the west or the east, but it depends on where you came from. So what we would say is that it's all relative. So maybe you've done something really, really tough before, but after you did the tough thing, you didn't think it was that tough anymore because you had gotten through it and you knew that you could succeed because you persevered. And so you might say now after the fact, like, oh, it's not that hard to run up that hill. Well, if you've practiced it many times, then you might believe that. And that's your perspective and from your point of view. And if someone else who has never ever ran before wants to run up the hill, it's going to be very, very challenging for them. And so the challenge is relative to who it is that's going to try to accomplish the challenge. And so this idea of relativity, it depends on who you are and what your perspective is. So let's dig in a little bit more. Let's start here with Einstein's theory of special relativity. Now, this basically just kind of relates to our last example, and it's the idea that motion is always relative. So I could ask you right now, are you moving as you're watching this video? And you might be moving your arms or your legs, but just in your position in the classroom, you're probably not moving within the classroom. And so if we look at it in the frame of the classroom, it's relative to the classroom, you're not moving. If we think about, are you moving in relation to the school? No, you're not moving relative to the school. Are you moving in relation to Fort Collins? No, you're not moving in relation to Fort Collins. Are you moving in relation to the universe or the sun? Yes, you are moving. You are currently being hurtled around the sun while the earth is on its orbit around the sun. So we are moving, but it depends your perspective and your frame of reference. So let's take a look here on this train. So if we have a train that is constantly moving at, let's say, 30 miles per hour, we could have some people on the train that are playing ping pong. Now, when they're hitting this ball back and forth, they might be hitting it back and forth with 5 miles per hour of force. And they don't notice this ball moving any different than this 5 miles an hour. But if you were this observer over here and you're looking at the situation, when the ball is moving at the same direction as the speed, it would be 30 miles per hour of the speed of the train, plus you would see the extra 5 miles an hour of the ball. So that person would think that they were seeing the ball travel at 35 miles per hour. But that's from their perspective, just standing here observing. The people on the train, though, they're only seeing it travel at 5 miles per hour. Now, the same thing would be true here. If these two ninjas were going crazy on the train, maybe they're just battling or practicing or filming a movie or something. This Ninja A, is trying to kick Ninja B, and Ninja B is not moving in relation to Ninja A. But if you were to ask our observer over here, Mr. Star Hat homie, if Ninja B was moving, he would say, yes, of course, Ninja B is in motion. If you asked Ninja A, though, no, Ninja B is not in motion. Because in relation to Ninja A, Ninja B is not in motion. Just getting ready to block that kick. Look at that. Watch out, Ninja B. All right, so special relativity is essentially saying motion is always relative. So if we're going to talk about motion, we have to talk about the situation. All right, well, there's a second theory of relativity, and that is the general relativity. And this is something that we talked about as we learned about gravity. And essentially, this is just the idea that massive objects warp space-time. Massive objects warp space-time. Now again, let's just remember, space-time is in relation to each other. So if you want to know where something is, you have to know the space or the place and the timing of that occurrence to really know where something is. So space-time is really two things that are relative to each other. They are connected to each other, space and time, in order to know where something is. So basically, if you have a massive object, it's going to warp the space-time, just like down here in this diagram that I drew that we're all really familiar with now. It's just this idea that objects warp space-time, but if it warps space-time, there's some really, really crazy mind-blowing things then that we can try to delve into if we do a couple thought experiments. So let's dig in. Okay, so one thing that Einstein realized then is that light then, as it travels through space-time, as it goes closer and closer to different objects, it's actually bent by the object, because if you think about the object, it's warping space-time, and so as the light particle travels, it's going to get bent. And so what we could say then too is that something that's bigger is going to bend light more than something that is smaller. So light is bent in the presence of gravity. Now this is actually observable by our sun. We can actually see stars that are behind our sun that we can't see through the sun, but since the light is bent, we can actually still see the light from those stars that would be hiding behind our sun. And the Earth does affect light a little bit. It does pull some light around it. It does bend light, but not as much as our sun would, because our sun is much more massive. All right, our second mind-blowing fact now is that time actually is also affected by gravity. And this here is just, you better put your hand on your head so you don't lose any brain cells, because this one's going to just blow your lid here. Get this, time will actually slow. Time slows down as you get closer to the source of gravity. That means then time speeds up as you get further from the source of gravity. That's worth repeating. Time slows down when you get closer to a source of gravity. It slows. So here on Earth, time would be slower than if you were to go further and further away from the Earth. Time would actually speed up. So time speeds up as you get further from the source of gravity. Now, this actually could be tested. We could put a clock on the top of Mount Everest. And we could also put a clock down here at sea level. So this would be tens of thousands of feet difference in elevation. So therefore, we would see a difference in gravity, because one of them is closer to the core of the Earth. So this one would have more gravity. This one would have less gravity. So therefore, if there's less gravity, then time speeds up. When there's more gravity, time slows down. So if we place those clocks on Mount Everest and at sea level on the very first instant that the Earth was considered to be our Earth, so let's call that day 1 of Earth, the very, very first instance where we had this. If we put a clock at the elevation of Mount Everest and one at sea level, the one that is up at Mount Everest would be 39 hours faster. So this one would look like it was in the future compared to this other clock. This one would appear to be slower. So this one would actually be just over a day and a half ahead of the one that was at sea level. That's pretty wild. Now let's expand this even further. If you were out traveling and you put on your Super X cape here, if you traveled at the speed of light for 3 whole years, so if you're traveling here at the speed of light, then basically it's going to appear, if you watch your clock, that 3 years have passed. And if you've got your buddy on the phone and you're calling them up to ask what's going on, say you got this extra phone, it fits in your pocket, you got your little wireless thing or your wired talkie thing that you can get out, and you call planet Earth and you say, hey, what's going on? What have you been up to for the last 3 years? Well, this person be like, 3 years? What? No way. I've experienced 60 years since you've been gone. And this person will argue, no, I've only been gone for 3 years. But this person is traveling at the speed of light, so therefore time is going to go much, much slower. And it would go faster if you were near the source of gravity, which is the Earth, and time would travel and you would experience 60 years. That's right. So all this information is things that relate back to Einstein's theories of relativity, the difference between and the combination of special relativity and general relativity allows us to think way beyond ourselves here on planet Earth. And if this is interesting to you, then you should follow the path of astrophysics as you continue on in your life. All right, anyway, I'm out of here. See ya.